Good afternoon. This is July 10th, 19, 2025, Fanshawe College, London, Ontario, ELEC 1013 network cabling class. All right, so today we're going to talk about the category cabling. Yeah, come on. Where's my red dot? There it is. All right. First, opening screen right off the bat. Um, I don't have reference for this photograph because I don't need to, because this is a picture I took. So there you go. Now, if this were data cables, they are not data cables, but let's pretend that they are. If there were data cables, can you spot any cabling faults here? Any installation faults? Anything wrong with this picture? Um, yeah, it's not easy to spot if you're not in the topic just yet, as far as the experience and so on. Notice how these bindings looks like some sort of twisties or something like that. Look as they are deforming the cable, they are squishing the cable. Cables are not supposed to be squished. All right. Now, within some companies, there's a hard rule of not using even zip ties with data cabling all across the board. All employees are not supposed to use zip ties with data cables. There are some companies that they're strict about that. Problem with using zip ties and twisty things like this is that you're deforming cable. You're making micro bands, and let me explain to you what a micro band is. This is picture from the previous class today. All right, well, there's a cable, and let's say there is a room here. There's a room, and here is the LAN room. There's a big room. Here's a LAN room, and you need to run the cable inside the ceiling. From the ceiling, you just go that way, and you go that way, and let's say you go right onto some sort of a desktop somewhere, maybe with the pack pole or something like this. This here, all right, that's macro band. You can't escape those. They will be there because you have to run cables somehow, and they're going to take turns. So if you're taking a turn like that with the cable, it's called a macro band. But if there is a cable somewhere in the ceiling, right, and if you put some sort of I don't know, let's just get silly and say you put a pencil. Here's the eraser of a pencil, and here is the writing thing here. That pencil, and if you put some weight on that pencil, this pencil is going to create some kind of an indent in the cable if it was here, like right there. That's called a micro band. If the microbands could be anything, could be a cable pressing on another cable. Like, for example, where could I see a possibility? Oh, right here. Let's say right in this spot right here. Yellow cables here. You see this cable here is kind of pressed by that one. Can we see other things? Right in here, this cable right there, this one is pressing on that one, creating a microband. That's why in some cases there are a couple of schools. One school says that you're supposed to make a mess out of the cables to avoid the crosstalk, uh, because if you run them just like nicely right beside each other, you could create a possibility of a crosstalk. I've never seen a crosstalk happening like that when cables are nice and straight. Although, to be honest, I was talking to some people in the industry. I've put up put in about more than 30 years working in the field. Other people put up about the same amount of time. And one person said that once they had, within the 30 years of their working, there was a situation the crosstalk has happened because two data cables were straight beside each other. Now, mm, crosstalk can happen, but also when you make a mess out of cables just like randomly arranged, you could probably create more damage by doing microbands in the cables. And binding them like this, you also can create microbands. Microbands are destructive because towards the signal, because by deforming the cables and maybe if somebody even steps on a cable, Cat 5e, if you step on it, walk over it, it will forgive you up to some point. Cat 6 and up will have no mercy on you. You step on that cable, you deform it, that thing changes its specifications, and it is better to just to make sure that there's no any problems with the signal. So the cable certifies as Cat 6. It's better to just pull it out and run another cable in its place. So you gotta be really, really careful when you're doing things when you're working on the construction sites, when you are laying cables on the floor to pull up some kind of extra slack because you have to pull cable from one place to another and you have to have some kind of an intermediate location. So you pull a slack on that, make a loop, and then keep pulling because you have to go over some obstacles or something like that. In that case, just have a person standing there, right where the cable is bound on the floor, uh, so nobody walks over it or drives over or rides over with some cart with wheels that are uh, basically if they ride over that cable, it's the cable is gone, right? It is how important that thing is. So what we're supposed to use? We're supposed to use Velcro. Okay? Data cable bundles should be bound with Velcro tape, and to make sure that things are nice and beautiful, soft side in. So the soft side of the Velcro is touching, making contact with the cables. Here are some examples of Velcro. You can buy them you can buy Velcro in bulk with this width or whatever it is, half an inch, 3/4 of an inch, or you can buy them with 2-inch wide, which also works nicely if you want to mount some lightweight devices right on the wall. But here's an example of binding data cables with Velcro. And over here, this is, I got this picture from the internet somewhere, and I noticed something wrong also with this, but I decided to keep it just so we could explain some things. Did I say soft side in? Look, this is not soft side in here, all right? So there you go. Soft side in is supposed to be there. All right. Now, let's imagine that this is a conductor that conducts electricity, all right? Electricity. Um, let's just imagine that it's connected to some circuitry over here, and it's connected further to some further circuitry and making a proper closed loop so the electricity flows through it. Let's assume the conventional current flow and just as a reminder, during the conventional, if we take the conventional current flow, the current is assumed to have a direction from the more positive side of the circuit to the more negative side of the circuit, unless it's in the power supply, because when it flows through the power supply, then conventional current flow will flow from the negative power supply. So just so I don't let's say here is a power supply, positive, all right, of course, and this is negative terminal, and here is a resistor, all right. So conventional current flows from the positive side of the circuit to the negative side of the circuit. And what I mean, unless it's a power supply, because inside that power supply, it of course flows from the negative terminal to the positive inside the power supply. So that's what I meant. All right. So let's imagine that there is a current flowing through this circuit. And when the current flows through this circuit, there is something that's called a magnetic field and electric field. So we call it electromagnetic field. So this arrow is pointing towards the electric field direction, and there is a spinning magnetic field around that conductor. What would be the direction of the current, or what would be the direction of the spin? Well, imagine a corkscrew, right? When you want to open your favorite bottle of wine, or maybe some sort of a cherry juice or something like that, that is plugged up with a cork. Here's a corkscrew. When you are turning the corkscrew towards the right, like the righty-tighty, that corkscrew is going to move in this direction, which means in the direction of the conventional current flow, and the direction of the spinach, if that's a word, is going to give you the direction of the magnetic field, okay? If you put another conductor in close proximity to that active conductor, and this could be an inactive conductor, which means it's not connected to any power supply. It could be connected to a just resistor, and that's it. But this wire is not powered by the means of induction, because if that wire finds itself within close proximity so that the magnetic field around it is strong enough, it is going to induce a electric current in this other conductor. The secret of that, the key to it, is that the magnetic field has to be changing. So Faraday's law, basically, when there's a change in magnetic field around the conductor, a current is going to be induced. So it's not going to work with DC unless if it's a DC current flowing through it, there's going to be a short burst of current at the moment of bringing that in. So the magnetic field around this conductor is going to change momentarily. But if the current is DC, so there's no change, then the current is not going to flow in the other conductor. But if it's an AC, then by all means, the induction is going to happen, because the magnetic field is going to increase and collapse and increase, build up and collapse. So there's going to be a constant change. This magnetic field is never going to stay the same. It's constantly going to be changing, and this conductor is going to be subjected to the changes of magnetic field, which means the current is going to be induced in that. Well, what's an audio signal or data signal? It's a constantly things going up and down, right? It just goes like this. So there's a possibility of something that's called a crosstalk, which means a signal is bleeding from one pair to another, from one conductor to another. And as the induction is something that works for us when we talk about transformers, because this is what we want, then when it comes to signals or signal wires and pairs, we kind of don't want that to be happening, okay? All right, so let's see crosstalk. In electronics, crosstalk is any phenomenon by which a signal transmitted on one circuit or channel of a transmission system creates an undesired effect in another circuit or channel, which means one pair signal flowing through one pair is affecting the other signal in the other pair of conductors. Crosstalk is usually caused by undesired capacitive, inductive, or conductive coupling, which is joining from one circuit or channel to another. There's a bit of a mouthful, but if you care to analyze that, it can open up a bunch of um, possibilities to expand your knowledge. This sentence looks like kind of quiet and you can just go by you. I would encourage you to study this, and that could be the eye of the fish. I'll tell you the story later. What the eye of the fish means, which means it's beginning to expand your knowledge. In short, but I'm not going to get into it because we have to carry on with the lesson. All right. In structured cabling, crosstalk is electromagnetic interference from one pair to another. In analog system, let's say there's a conversation going on between these two wonderful people. And at the same time, there's another conversation going on between these other two wonderful people. And if those cables run along, the connecting cables run along from one conversation and the other, if those cables run along for a certain distance, the magnetic field around those, they could couple with each other, which means one type of conversation could bleed on to the other pair. So these people can hear the conversation of these people. And sometimes, because I remember sort of towards late 80s and beginning of 90s, towards mid 90s, it was still possible to hear crosstalk on the phone. Now, these days, technology has gone a little bit further and got improved. There is no recent memory that I could ever experience of a crosstalk recently, which means I'm talking on the phone with someone and all of a sudden some other conversation just fades in. But a few years ago, not that long actually, it was possible to hear. It was a common problem. It could be caused by splitting pairs. What splitting pairs is, well, okay, just remind me to get back to it because I don't want to digress too much. In some cases, you could hear the other conversation, but you couldn't talk to the other people. But in some cases, the electromagnetic coupling would be so strong that you could actually have a conversation with the other two parties. As I said, right now, it's not happening that much, if at all. Now, what would be splitting pairs? Splitting pairs. Let me just get a better color here. Yeah. Okay, come on. Give me a nice color. All right. Let's say there is a pair, is a trunk. Let's say there's a 25 pair cable. Make it shorter. There's a 25 pair cable having pairs. Okay. Da 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 da. Remember the color code. Let's say this is a blue pair right here. This one here. And let's say this here is an orange pair. So then the blue pair comes out the other end, and the orange pair among the other pairs comes the other end. And those cables have a twist. I'm just not drawing the twist. The purpose of the twist is that if you have two cables, if there is electromagnetic field that can build, and it could have strong effect on it have, because it's a constant electromagnetic or magnetic field built from one cable affecting the other, and if it runs over a certain distance, it could have enough energy to induce itself onto the other circuit. But if you have a twisted pair, let's say the pair is twisted, this magnetic field, it could be strong here and it could just go like that. So it's not going to have enough consistency to affect another twisted pair, which is beside it. Because that not only this here is going to be this original magnetic field is not going to be consistent enough, but the physical subjection towards the magnetic field is also going to be twisted. So there's not going to be consistency. So it's going to be difficult for that magnetic field to impose itself onto the other pair. So that's why we do have a twist. Now, sometimes what would happen is the telephone line trunk, because the 25 pair could be considered as a trunk, which consists of many pairs. And let's say the cable goes across the street and feeds some neighborhood with a few houses with the telephone lines. But for some reason, well, one of the circuits has stopped working. There could be a physical break somewhere inside this cable. Something could bite through it, or maybe there's some kind of landslide or whatever that would cause some sort of damage. So let's say this pair here, whatever color of that pair is, the client doesn't have a phone. It's broken somewhere. And the technician goes on one side, opens up the closet on the other side of the street, and they say, well, can we find another working pair so we could connect that client? And they say, oh, too bad, because all the other pairs are being used. We have no more free pairs left. So the techie what they would do sometimes, they would split the pairs. They would find one bad pair that was already marked as bad, and they would find another bad pair, and they would hope that maybe just one of those conductors is broken and the other was intact. So let's say this one is working, and that one is broken somewhere. All right. And let's say this one is working, and this one here is broken somewhere. So they would make one pair out of the two bad ones, just using the good conductors and abandoning the broken ones. But what happens in this case, you are losing the twist, okay? Because this pair is twisted around itself, the other pair is twisted around itself, and those two conductors are just like two straight wires to each other. So that's splitting pairs. You use one conductor from one pair, another conductor from, and do the same thing on the other side in order to have the client some connection. And then you could let the office know, or whatever the company, that this is what you've done, and maybe we need to have some crews going there and pull some more wires because we have no more free. So that's called splitting pairs. And that would cause definitely that would cause a crosstalk between other pairs. Splitting pairs. All right. Here is a little video that I'm not going to play that. I'm going to ask you to play it once you download this presentation. Basically, there's a person that is showing two data wires being brought closer together, and they're so close, and the signal within those data wires is strong enough that is able to knock the other transmission out of line. So that's when two wires are brought together close enough in a digital transmission. In analog transmission, let's say there's a TV station that's being picked up by antenna, and not too far, there could be in proximity close enough, there would be another TV station that is transmitting on similar frequency, and somehow the signals start interfering. And if you're watching your favorite hockey game on TV, and there's some sort of other programming that kind of bleeds through, fades in little bit, and making the hockey game not really clear for you to view, you might get annoyed. But you still, if you really want to know what's going on with the hockey game, you would still be able to watch. Not a good quality picture, but you still know what's happening. That's analog. Now, digital, if there is interference, the signal just dies out. Let me explain why this is happening. Let's say there is one transmission channel that goes towards the destination here, and another transmission channel, and here is its destination. Here's the receiver, here's the transmitter. Now, in digital transmission, what we have is we have ones and zeros transmitted. So like, let's say 5 and 0 volts, and so on. And the transmission is divided, it's supposed to be a straight line, into time intervals, okay? Equal time intervals. So let's say there is a, whatever it is, the signal that says start listening now. Then, because the timing wise, the transmitter and the receiver, they have to be synchronized with each other. But you cannot synchronize them with the same time, because it takes some time for the signal to go from one end to reach the other end. It's called a propagation delay. So what happens is that the transmitter and receiver are synchronized in a way that they synchronize with the same baud rate, which means the same intervals of listening to the signal. So there's a signal that says start listening now, and if they are set to the same baud rate, same listening rate, same speed of listening, then when the signal gets to the other end, that receiver is going to listen with the same speed as this one is transmitted, and it's going to receive the ones and zeros where there's supposed to be ones and zeros, and it's going to be able to recreate the signal and do something with it. It's going to be, in short, it's going to understand the signal. Now, if there is another signal, strong signal, that produces other interference, it could be another digital signal, or it could be just a strong interference from some sort of a fluorescent light, ballast, or whatever else. And if that circuit is in close proximity, that line, it's in close proximity to the other one, it is going to, what is it going to do? It is going to introduce different levels at different times. All right. And those are going to combine. So this proper signal and this interference are going to get there as completely something else. This receiver, there's no way it will be able to interpret high or low at the same time. And he's going to say, I don't know what this one is saying, so I'm just going to shut down. And so in digital transmission, interference will completely kill the transmission. In analog, you could get annoyed, but you could still, I wouldn't say enjoy, but you could still, for the most part, could get your message that you're supposed to get. Watch that little video here. Now, I'm just going to say it's a bit of extreme because, well, look. Over here, let's say there will be data cables. You're going to see something like that. So you're going to say, you can say, oh, what's Bach talking about? Because, well, on one hand, I'm showing you that there's just two cables close to each other and the signal dies out. And here is a bunch of cables close to each other. How come the signal doesn't die out? Well, as I said, that is an extreme. It just shows that sometimes we need to use the cables that are shielded. All right. Now, let's talk about something that's called a UTP, and the UTP stands for unshielded twisted pair. So, there you go. Here's Cat6 cable as opposed to Cat5e. There's a helicopter that's flying by, and I wonder if you can hear it or not. It could be a noise cancellation routine going on. But anyways, okay, it's gone. I can concentrate now. All right, so you see here, the pairs are twisted. So the magnetic field around each pair cannot build up the consistency and thus the power or having the energy to impose itself into another pair. Now, each pair is twisted at a different rate. So even if you have one twisted pair, and if there would be another twisted pair that's twisted at the same rate, they could align physically and the coupling would take place. But no. We're twisting those pairs at different rates. So whichever way they're going to be positioned lengthwise, they're not going to synchronize physically, and thus they're not going to synchronize or have the magnetic coupling or electromagnetic coupling from one pair to another. So that's Cat5 or Cat5e. Now, Cat6, how you can tell, is Cat6 has Cat6 cable, has this here plastic separator in there. And look, each pair has its own groove in that separator. So not only the pairs are twisted, plus the pairs are twisted at different rates, plus the separator, as it travels along, the separator is twisting itself as well. So there is a triple whammy going on there. All this is to eliminate the possibility of crosstalk, which would be signal bleeding from one pair to another through the phenomenon that's called induction. And believe it or not, the concept of twisted pair was invented by Who else but Mr. Alexander Graham Bell in the early telephone days? And this is just a bit of a magnification to show that pairs are twisted at different rates. The purpose of the twist is to eliminate crosstalk between pairs. Now, my throat is drying out. Hold on. Sip of coffee. From unshielded twisted pair, let's go to shielded twisted pair. Shielded, twisted pair. There you go. And that's what it looks like. Now, there are different types of shielded twisted pair. But first, what's the purpose of shielding? Well, in certain environments, such as industrial environment, for sure, when you have to run the cables, not just in the ceiling, that you have to just in the ceiling or in the walls. In the ceiling, you just have to avoid some fluorescent light fixtures or some other cabling, especially fire alarm cables and security alarm cables, because those are the biggest noisemakers. As far as the electromagnetic interference, so stay away from those. The rule of thumb would be about a foot distance from any other cabling that's happening. Right? But in some industrial environments, such as machinery, some of the machines have control modules, and those control modules have to be connected with, well, Ethernet cable. The machines do have electric motors running. There will be some other switches and relays clicking on, clicking off, so that those spikes can introduce themselves within that digital transmission and can kill the communication between the modules. So when it comes to industrial machinery, the modules would have to have some extra protection, especially from the outside interference. Now, there are different types of shielding as far as the cables. Now, let's just read what I wrote a couple years ago. Although unshielded twisted pair cable is the least expensive cable, it might be susceptible to radio and electrical frequency interference. It should not be too close to electric motors, fluorescent lights, and so on. But if it comes to machinery, you can't have it far from electric motors because it's all there. Right? In presence of high interference, shielded twisted pair might have to be used. And now, the types of shielding on cables. You could have each pair of wires individually shielded with a foil. Or you could have one common foil or braided shield just covering all those pairs. Or you could have each individual pair shielded, and on top of that, one more common shield that embraces all of them. So that's in cases of strong interference. Now, these cables are more expensive, and the jacks and paraphernalia is more expensive, and installation is more expensive because it takes more time to install that. And you have to pay close attention to where you want, because this here, it's the shield wire that is kind of wrapped around the shielding, and it has to be grounded. And sometimes the situation calls for one side to be grounded. Sometimes the situation calls for the other side to be grounded. But for the most part, both sides have to be grounded. Although sometimes you just want one side to be grounded, because if there is a possibility of those two grounds being at a different potential, then you could end up with something that's called a ground loop. And that would be even worse than having no shield. Okay. So depending on situation, you have to pay attention of what the instructions for the installations are. Now, before we move on to the next slide, I'm going to have this as a pre-slide explaining what the CCA stands for. So when I talk about the CCA, you know what I'm talking about. It's not just an acronym. CCA stands for copper, clad, aluminum. Clad is just like surrounding, wrapping. Aluminum wrapped with copper, okay? When you magnify those little conductors, they would look like this. Here's an aluminum wire, and it's just coated with copper. In order to pretend to cheat the signal, to think that it's running through a copper wire. Somewhat not bad of an idea in theory. In practice, it's a total failure. However, for some reason, not understood by me, this cable is still being sold at extremely cheap price, way cheaper than BC, which stands for bare copper, which is the whole copper. If you see that, if you see some box of wire or the price of the wires that you buy when you're buying wiring, the cables, when you see that at some kind of extremely low price, unusually low price, check if it is CCA. And if it is, please do yourself a favor and do not take it even if somebody gives it to you free. Why is it that I wouldn't want to even take it free? Well, first, it is a disaster when you're trying to install network cabling with that. Nothing but problems. This cable is basically breaking as you're punching it. And once you punch it, there is no guarantee that it stays in the connectors properly. So it's even worse than having a no connection, because a connection that is unreliable is worse than not having a connection, because when you have no connection, you know things are not connected. When you have unreliable connection, you think you're connected, but you're not. So why wouldn't I take it free? Because even junkyards don't want that. So you're stuck with it. Can't use it for work, can't dispose of it in a junkyard. Right? And for some reason, this thing is still being sold. So stay away from that. Now, you could see sometimes the CCA cable is being used. If you look at some of the expensive headphones, like expensive, $200 and up. If you look at the specifications, type of the wire that is used for the coils for those little ear speakers there is CCA to save the weight. However, that CCA wire is done in an industrial way by machines and all that stuff, and nobody has to go in it, taking in, taking out. It's just sealed and it's there, and just saves the weight. Now, you want to keep that table here. There's two cables that I did not list, and I'll tell you about. There's different categories of cable, Cat5, Cat5e, Cat6, and so on. Over here is the gauge of the wire, American wiring gauge, which is the thickness of the wire. And over here, you can see the wire has a certain thickness. There's a wire has a certain thickness of gauge 24. Now, Cat6, the wire gets thicker because the gauge numbers get smaller. Here's the twist, transfer speed, maximum length, bandwidth, and applications. So let's take a look at Cat5. Let's move on to the last column here. Obsolete, not used anymore. Doesn't mean that you're not going to see it, because in some installations, you're going to see some of the old installation, and the old computer network still works on Cat5. But if you want to install a VoIP telephone system, And if you want to use the existing data wiring, you can't because it's Cat5. VoIP telephone system will not work on anything less than Cat5e. Right? So Cat5, when you see it, and if you need to install a VoIP telephone system, you have to tell the client that, look, yes, we can install this for you, but we have to replace the wire from the switch to the desktop. And of course, it's going to cost the client money. Now, the gauge of the conductor for Cat5 is 24. Twist, it does have a twist. The transfer speed versus the bandwidth. Transfer speed has 100 megabits per second. And the bandwidth is 100 megahertz. It just so happens though those two numbers are the same in this case here. I'm going to continue with this lesson, although we're running out of time. So if you have to go to another class or something like that, please go. I'm not going to hold you. Once I post it on YouTube, you're going to be able to catch the end of it. Okay? I just want to get caught up on this. So I might be talking to myself for the next 15 minutes. But you're welcome to stay. Here's Cat5, 24 gauge conductors. It has a twist. The transfer speed is 100 megabits per second, and I'm stressing it out. When it comes to signal speed, transfer speed of the signal, data, digital signal in the wire, we're talking about bits per second, not bytes. Bits. Bytes is reserved for storage. Let's say this hard drive is capable of storing 1 terabyte, and it, of course, it's not per second. It's just terabyte of storage. But when it comes to transfer speed, we're talking about bits. So here's 100 megabits per second of a transfer speed. Now, bandwidth is measured in hertz. So Cat5, not Cat5e, Cat5 is able to carry 100 megahertz of a frequency. And if you modulate that frequency in some way, that frequency can be transferred from one end to the other in the cable, and still the shape of the signal can be understood up to 100 megahertz. And it can send the bits, the digital pulses at the rate of 100 megabits per second, and the signal still will be understood on the other end of the cable. The maximum length of Cat5 is 300 feet, which is pretty much, and I have to say that quote unquote pretty much, because something has happened in the industry that just changed the whole thing. But I'll talk about that. But for the most part, 300 feet is the furthest you can carry data signal. All right. Let's take a look at Cat5e. The gauge of the conductors is 24. There is a bit of a tighter twist. The transfer speed is 1 gigabit per second instead of 1 megabit per second. That's, 100 megabits. Okay. Distance is the same. Now here's the bandwidth. Here's the digital signal, bits per second. And here is the analog capability of carrying analog signal of whatever the frequency would be. Now, Cat5e can carry up to 100 megahertz if it's CCA, which is the copper-clad aluminum. And it can carry up to 350 megahertz if it's a bare copper, which means basically the whole conductor is out of copper, not aluminum coated with copper. Applications, home networks, small offices, commercial. Now, Cat6, I'm not going to go through all of them. I'm going to stop about Cat6 here. Cat6, you see the gauge, the wires are becoming thicker because it's gauge 23 as opposed to 24. It has a tighter twist. It does have that separator. Now, the transfer speed of the signal, excuse me, the transfer speed of the signal is 1 gigabit per second up to 300 feet. And if you're installing this as a Ethernet network, it's no different than Cat5e, up to 300 feet. But if the distance is less than 180 feet, then you can get signal speed of 10 gigabits per second. And here is the bandwidth in megahertz. So if a client wants to get a good cable, it would be like this. Is Cat6 better than Cat5e? Well, yes, but. Oh, here's the but. Okay. But what? Well, how long are your runs? Let me see the building. Let me see where things have to be run from and to. Just to make sure that if you get Cat6 installed, you get the benefit of Cat6. Otherwise, if the runs are longer than 180 feet, you might as well get Cat5e. But there's one more but. Because Cat5e was quite popular until about now, or maybe a year ago. And Cat6 would be way more expensive than Cat5e, so Cat5e would hold strong ground as far as being used for the money. But now the technology has improved to a little bit more advanced stages. That Cat6 has become not as expensive comparing to Cat5e anymore. So it's kind of pushing out Cat5e. So most of the time you're going to have Cat6. In fact, in some distributors, it's hard to get Cat5e anymore. You're just getting Cat6. Well, just as long as you understand that if you want Cat6 benefits of Cat6, then you're going to have the runs of no longer than 180 feet when you want to get the 10 gigabits signal transfer through that cable. Right? However, there's one more but. Well, but before I get to it, if you want, within this system here, if you want the full benefit of 10 gigabits per second for 300 feet, you're going to have to get Cat6a. The Cat5e, for example, the E stands for enhanced. And this Cat6, the A stands for amended, which means enhanced. Now, Cat6a, way more expensive, way heavier. The thickness of the cable is comparable to a coaxial cable, while Cat5e and Cat6 are not as thick. So it's harder to run, because if you just want to run one wire from one place to another, no big deal. But if you have to run 600 of those, then you're going to bundle them up in maybe 10, 12 wires each bundle, and pull them in one bundle. Much heavier to pull. Way more fragile as far as sensitivity to physical damage. You can damage all cables, but Cat5e can forgive you some damages. Cat6 will have no mercy on you. And Cat6a will no mercy on the mercy that would have been on you. Don't ask me to repeat that. Right. So it's way more expensive. The jacks and the paraphernalia is way more expensive, and it takes even longer to install. There is also something that's called Cat6e, but I was trying to find some solid specifications for that, consistent specifications, and I can't. Different sources give me different specifications. So Cat6e exists. Believe it or not, it exists. I've seen it with my own two eyes that it exists. My eyes got bigger when I saw it because I never thought it existed, and some people still didn't think that it existed. But yes, it exists. As far as specs, there would be some, the best answer from anybody or any sources I could get is, yeah, the specs are somewhere between Cat 6 and Cat 6a. Well, that's not very specific specifications, right? I've never had a chance to install Cat 6e ever in my over 30 years experience in this business heavily. I have seen Cat 5, I've done Cat 5, I've done Cat 5e, I've done Cat 6, I've done Cat 6a, I've done Cat 7, and the fiber. Because after Cat 6a, do you really want to bother with Ethernet? You might as well go with fiber. But that's my opinion. Could be, the reasoning could be different for whatever reason. So Cat 6a was going to give you the 10 gigabits per second for full 300 feet. So here's the last but on this page. I don't know, 2 years ago or something like that. This is 2025. There's another cable that was introduced on the market. And I'm talking to people, and I haven't heard of anybody using that yet, although it exists. It's a game changer. And it's a game changer, and the name of the cable is actually called, the official name of the cable is a game changer, because it is a game changer and it was named a game changer. It's a cable, it's an Ethernet cable that is going to give you Cat 6, well, Cat 6a specifications. I'm not sure about the bandwidth, but as far as it's going to give you 10 gigabits over 1,000 feet. To someone who has spent over 30 years in this business, it is a huge game changer, because every installation would hover around the 300 feet, everything would be with the 300 feet in mind. Actually, it's 328 feet, but you don't want to install 328 feet end to end, because you still have to use the patch cords to connect from the jack or the outlet to the PC or whatever else device. So yes, there's a cable that exists that can go up to 1,000 feet with 10 gigabits per second transfer. You might want to keep that, this page here. Now, let's see some wiring details. As we know from our labs, this is just kind of like putting this thing all together in the theory class. This is an RJ45 jack or plug, and here's the pin numbers. If you hold it like this, and the pin, the little latching clip is facing away from you, this is how you're counting the pins. 1, 2, 3, 4, 5, 6, 7, 8, from this side to that side. However, this is not how we count the pairs. Remember, pair 1 is always in the middle. So it will be pin 4 and pin 5. And this is where the telephone if a telephone signal was run through it instead of Ethernet, this was where the telephone would look for. The telephone cable would look for the signal for line 1. And usually it would be just line 1, only one line. How is it that we are counting the pairs? Like this. Now here, still one thing here. See, I'm just counting it from this way here, from the bottom to the top, because that's the positioning of the jack or the plug. And the table is counting those pairs a little bit different from top to bottom. So just kind of adjust with that, right? This is how we count the pairs. Here is, well, remember the colors? Blue, orange, green, brown. All right. Here's the blue in the middle, pin 4 and 5, where the solid goes blue, solid goes, well, is this correct here? Yes, it is. Yeah. Because you see, the stripes are going that way in all the pairs, except for the blue pair, the stripe goes that way and the solid is on this side. Don't ask me why, but it's just how it is. So pair 1, here's pair 2, here's pair 3, and here's pair 4. Blue, orange, green, and brown. Remember the dance that we did? If you had this jack and you turn it this way, so this is on top, like that. Here, if you turn it 90 degrees, it will be blue, orange, green, and brown. That will be the dance that I did for you. Remember? Now, here's a typical connection for Cat5e. Cat5e uses only 2 pairs. The orange pair and the green pair, and the blues and the browns are not being used. In fact, you can get some cheap patch cords that are labeled as, that are basically rated Cat5e, and you're going to have the blue pair and the brown pair just not there, missing, empty prongs. Sometimes you can get that. But usually, if it's a patch cord, it's a patch cord. It's rated either Cat6 or Cat5e or Cat7. And usually all of them are there. But if you see that cable with some wires missing, that's for sure going to be Cat5e. One is transmit. One is receive. Which is which? Well, which is whistling, which is not. Okay. Here's the network interface card, NIC. MDI. Medium dependent interface. What's a medium? Well, air? No. It's copper in this case. That will be the medium. So it's depending on the copper connection. Network interface card is in your laptop, in your PC, and it could be also a wireless network interface card in your cell phone, but we're not talking about that. We're talking about hardwire connection. And then here's the port on the hub or switch. This is the LAN side, local area network side. That's the equipment rack side. The terminals on the NIC, network interface card, on your PC or laptop are arranged in this way. The pin 1 and pin 2 are the transmit pin. That is to be connected to the receive pin, and that's how they are arranged, those terminals. And transmit on that one here, this hub or switch, is connected to the receive pair. So the communication going this way and the communication is going that way. There's both ways communication at the same time. And the ports are wired in a way that then all the NICs and all the hubs and switches are wired in such way that they are supposed to be connected with a straight link. All right. Now, here is, as opposed to straight link, here's a crossover link, and we are already basically dealing as we speak this week, class of 2025, summer network cabling course. It just so happens that we are doing this lab right now, this week. We're creating a crossover connection. Let's say you want to connect two PCs together. Now, these ports are the same. Those ports are not as the hub or a switch. You see, on a hub or a switch, pin 1 and pin 2 are receive. And on a PC, pin 1 and pin 2 are transmit, just like here. Like these are two of those connected. You can't connect them with a straight link because you'll be connecting transmit terminals to transmit terminals. They're both going to be talking at the same time, no communication. And you will be connecting receive to receive both at the same time with a straight link. They would both be listening at the same time. Again, there's no communication. So you need to connect the talker to the listener. If those terminals are the same, because PC and a PC, then you have to rearrange those wires so the transmit is connected to the receive terminals, and the receive terminals is connected to the transmit terminals on the other terminal. So that's why we need to have cross. I just scared myself touching the microphone. So that's why sometimes we need to make use of a crossover link, and usually that will be a patch cord. Okay. And does it look familiar for people who already have done the labs? Look, here's the one end, here's the other end. Oranges and greens are being, look, pin 1 connected to pin 3, pin 1 connected to pin 3, and so on. All right. And the blues and the browns are going straight through Cat5e. When you're testing that, in some testers, it's going to show us failure. That's where the X is. X means a failure. Yeah, very much. But we are looking for a certain type of a failure. And in fact, it shows. It failed a straight link test, but you are actually having an A to B connection of the T568 standard, A to B crossover. So it fails in a certain specific way. That's what we're looking for in our testing. Now, here is a picture and a half. If you Google crossover Ethernet link and click images. Excuse me. And click images. You're going to get two types of pictures. You're going to have some form of this, maybe with some blues drawn straight and the browns drawn straight. And you're going to have some version of this type of picture, and they're both going to be named as crossover Ethernet link. And you might think to yourself, how did I get here? No, that was a song. You might think to yourself, did somebody make a mistake? Or is there some kind of a false information, fake news, or whatnot? What's going on? They both look different connections, and they're both labeled as crossover links. No, nobody made a mistake. It's just sometimes people do not explain things fully. Right? Up to Cat5e, only two pairs are being used, which is the green and an orange. So if you want to make a crossover cable, you just have to cross the oranges and greens and leave the other ones intact. You're still terminating them when they're there, or not if they're not there, but that's all you have to cross is the transmit and receive, because only two pairs are being used in Cat5e, up to Cat5e. Now, beginning with Cat6, all four pairs are being used, which means you have to cross the oranges and the greens, and you also have to cross the browns and the blues. Mystery solved. That's why you're going to see different. Cat6 and up, all four pairs are being used. Cat up to Cat5e, only two pairs are being used. Once I had a situation that the instruction was install the cameras, so remove all the old security cameras, install new security cameras, use the existing Cat5e wiring, and if you have, replace the wiring only if you have to. So I had to go and do the testing first with the tester to see if the cable is, pass or fail, lengthwise, wire mapping, and all the little frequency response or whatnot. And one cable gave me grief. It came up as a failure, one broken wire. So I looked at the wire map of whatever it was a straight link, and I asked myself, which wire is it broken? It turned out to be the brown wire that was broken. And that was a Cat5e configurations. Those security cameras used Cat5e. So I go, well, even though the cable failed, the two pairs that are being used are intact. It's just that unused pair is broken somewhere. And of course, the professional response to that type of situation would be, because you were instructed only replace if necessary by the client. So I went to the client and I said, look, this cable there's a broken link there, but it's not a pair that's being used. There's no guarantee that maybe there is something crying on it, because in that case, there was some instances that the cable was covered somewhere and they would have to go and look around the corners and between things. So it was a difficult pull anyways. So I said, look, there's no guarantee. If you want, I can replace the whole cable, but the two pairs that are supposed to be working are working, so the camera is going to work. But don't know for how long. But if you want to replace the cable, it's going to cost you this much. The decision was leave it as it is, and if problem exists, if problem happens, then we're going to deal with that. You're clear with the client, nice and professional. that what make that it makes you kind of credible when your credibility um, is good. Your integrity is good when you talk like that. If you try to hide things, that's where you're going to be having some integrity problems, right? But thanks to that knowledge that it's got 5E and this came to fail, which is broken is brown, only greens and oranges are being used. I was able to use that knowledge to my advantage. And that's the last slide for today's class. Next time we're just going to talk about network types on Friday, and then we're going to enjoy yet another weekend. So it's almost Friday. Please enjoy the rest of the week. And if somebody can't come over on Friday, have a wonderful weekend. That's it for today. I'll see you when I see you. Thank you.